Yadum Ure Yavarum Kelir. That means we are all from the same family. We are all here for one purpose. And we are all going to treat each other as brothers and sisters. Having said that, I was here and I looked at this close by building, which is called the Gates Foundation, and I was struck by some of the images I saw. Great ideas come from everywhere, which goes with the theme which I mentioned. And we are here to invent new ways to solve old problems. What else can be an old problem than curing a disease? Because mankind has been fighting this from the day one. And this has been going on, and we are now approaching that, the old problem, with a new modality, namely oligonucleotide therapeutics. And that's what we are going to talk about. And we know DNA makes RNA, messenger RNA, and messenger RNA makes proteins. And the traditional approaches is to stop the function of these proteins by small molecules or biologics like antibodies. But in terms of the nucleic acid as medicine, it could be the same target in the protein target, where we can use aptamers, or the emerging therapeutics like mRNA therapeutics, where we are creating the protein needed for the function, or RNA activation, or immune modulation. Alternatively, we can go deep down into the DNA target itself, and we could do gene editing, CRISPR-Cas type mechanisms. And our field in the past 30 years have focused mainly on targeting mRNA, and mRNA target can be addressed by antisense oligonucleotides or RNAi siRNAs, and some of the RNAi cousins, namely RNAi pathway modulators like microRNA mimics or anti-microRNAs or antisense. And more importantly, in the RNAi pathways, controlling the pre-messenger RNA by splice switching oligos. So these are all the various mechanisms, and it is very difficult to bring all the mechanisms and all the chemistries into the next 16 minutes, but I will try. And in the first case, this oligonucleotide modalities can be either single-stranded, like in the case of antisense, or double-stranded, like in siRNAs. Here you can see this molecular weight is 7,000. Here it will be 14,000. We are dealing with the 19 formal negative charges, considering a 20-mer oligonucleotide. Here this will be like a 40 negative charges. This molecule is flexible with 1 nanometer width, and this molecule is being formed the helix. It is rigid with the 2 nanometers diameters. There is one physical property difference, because the aromatic bases are exposed in the single-stranded molecules because of the non-compactness, whereas in the double-stranded molecules, the aromatic bases are paired and buried inside the duplex, and this contributes to their protein binding and physical properties of these molecules. And we all know making drugs out of oligonucleotides is not easy because of the molecular weight, because of the size, and the larger size and negative charges. More importantly, they are hydrophilic and tend to, for this urinary excretion, they are hydrated heavily because of that poor protein binding properties, not distribution properties. On the top of it, biostability controlled by the endonucleases and exonucleases, and they tend to be substrates for immune activators like TLRs and so on. And these are all the challenges intrinsic, and then on the top of it, we are dealing with the delivery challenges, delivery to the right tissue, delivery to the right cell type, and delivery to the site of action. In the case of siRNAs, for example, in this cytoplasm, or SSOs in the nucleus, antisense in the nucleus. Having said all those challenges, we are so happy and proud to point out that we have 6 approved oligonucleotide therapeutics in the past 20 years. And these are Vitravine, antisense oligonucleotide, Mipomersin, antisense oligonucleotide, Macugen, aptamer, Spinraza, spin splicing oligonucleotide, and eteplirsen spin splicing oligonucleotide, and patisiran in the siRNA family. So these are the success over the past 20 years. So in the first compound, vitravine, which is the formiversin, this is the totally DNA phosphorothioate oligo 21mer, which is the sequence is shown here, and these are the linkages referring to as the phosphorothioate linkages. And these were early days when people didn't fully understand the immune stimulation mechanisms. You can immediately see here it's a CpG sitting at the very 5' end. And Art Craig will be talking about that in terms of contribution of these mechanisms. But these single-stranded molecules enter the nucleus and finds the messenger RNA target through the Watson-Crick base pairing, and then the duplex having the RNA DNA nature, and that chimeric construct recruits RNase H, and RNase H cuts this at the multiple sites, and it is degradation. Now this molecule is looking for the next copy of the messenger, then looks for recruiting the RNase H, and the cycle goes on. And this was the compound which was for controlling CMV retinitis, and this was administered intravitreally. And in both cases of antisense as well as in siRNAs, as we know, we are killing the messenger. And this killing the messenger goes through a similar mechanism. It provides the 3' hydroxyl at the 5' end and 5' phosphate at the 3' end of the message. And this is a similar mechanism, but as I mentioned, it's multiple cuts in the antisense and single cut in the siRNA. And this is by looking back into the history, this is after 98 approval, the Time magazine's picture of this vitravine, which explains this controlling the CMV immediate early gene 2 for the treatment of CMV-induced retinitis. And this is the chemistry behind it, namely deoxyphosphorothioates. Although the very first compound was administered intravitreously into eyes, the PS chemistry is crucial for broad distribution of multiple generation of antisense oligonucleotides because it distributes the molecules to kidney, liver, spleen, bone marrow, adipose tissues, muscle, and others. And this is again looking back into the history. The people who contributed to the phosphorothioate oligonucleotides, Fritz Eckstein back in 1966, and in 84, Steck and Zahn developed the oligonucleotide synthesis at NIH. And this is a memo which I got from Steck in 98 after hearing the approval of vitravine, and delighted by the joy. And this phosphorothioate oligonucleotides, when we replace this phosphodiester, it can be either left-handed or the right-handed. As shown here, this is the RP isomer. This phosphorothioate linkage is sticking outside. The SP isomer, the phosphorothioate linkage is going inside, displacing the metal ions. And these are the properties which control the metabolic stability, treatment, the other enzymes, and the properties of this, and also treatment with dealing with RNase H. And when we incorporate these PS linkages, it results in 2^n diastereomers. So we are making a mixture of diastereomers, and this handedness is referred to as the RP and SP isomers. And as you know, now there is that tendency to make this chirally pure oligonucleotides. In addition to the deoxyphosphorothioates which activate RNase H, there is one other compound, namely 2'-fluoroarabinose can also activate RNase H. And I want to point out, these are configurational isomer of 2'-fluoro, not conformational isomers. And we are dealing with a fluoro up in the configurational status. And this has to be fully understood when we are dealing with the fluoro compounds. In moving from the first generation antisense to the second generation compounds, these are gapmers, which are having a 5-10-5 motifs. And this is this deoxy motif in the middle with the 10 nucleotides approximately number. It activates RNase H, and this methoxyethyl modification at the ends, at the wings. they provide the binding affinity and so on. And all these phosphorothioates, according to ISIS Ionis modifications, and these have this base modification of the C is having a 5-methyl group. And this is the approved compound mipomersin or Kinomera, showing the methoxyethyl at the wings and the gapmer deoxyphosphorothioate in, and then the 5-methyl C, which are either as a deoxys or methoxyethyls. And as I mentioned, the drug distribution is very important, and this is a lesson which I learned 20 or 25 years ago in Art's group, namely when the kid gets the injection in the rear, and he's wondering how that's going to cure his sore throat. So the drug has to distribute to the site where it is needed, and that is provided by the phosphorothioates. Whenever we make these modifications in the 2'-O-methyl or fluoro or methoxyethyl or LNA, BNA or C8, in all these cases, what we are doing is two things. We are making them into preferentially C3' endo, which is needed for binding to the RNA target. The second thing, the phosphorothioate provides broad distribution for antisense oligos or splice switching oligos. In the case of siRNAs, the phosphorothioates are not needed that much compared for the reasons which I will mention briefly. So summarizing the 2' modifications, it provides the binding affinity to RNA, provides metabolic stability. In addition to that, chemical stability compared to DNA during the synthesis, because it avoids the depurination. For the same reason, it enhances the metabolic stability in acidic compartments, and it modulates the hydration and protein binding in the case of methoxyethyl through this double gauche effect. Hydration occurs and also contributes to the hydrophobicity. 2'-O-methyl, 2'-fluoro, LNA, C8, they all increase the hydrophobicity, which may cause into the cellular uptake or endosomolytic release properties. Now let me move on to RNAi therapeutics. In the RNAi therapeutics, we are introducing a double-stranded molecule, and this is loaded into the RISC, and when loaded into the RISC, and it is the sense strand is removed, the antisense strand with the phosphate is loaded, and it is recognizes the messenger RNA target, binds, and then Argonaute cuts. The specificity comes from the 10th nucleotide from the 5' end, so specific cut. Now the drug molecule, the functional molecule, is loaded into the Argonaute, and it is can go catalytic function, can repeat several times. And that also contributes to the longer duration associated with the RNAi mechanism. And Alnylam has demonstrated this functional siRNA delivery to liver using 3 platforms. One is through the chemical modifications. The second one is through the lipid nanoparticles, which are capsulating these siRNA strands. The third one is taking the siRNAs and conjugating through the GalNAc at the 3' end. And this lipid nanoparticle things which you have to remember is administered intravenously. This is a formulation, and as demonstrated by Anpatro, this is clinically validated, and GalNAc is in not only for siRNAs, is useful for several oligonucleotides, and this is a single chemical entity administered subcutaneously, and this is also clinically validated because there is various advanced clinical trials are going on. And starting with the lipid nanoparticles mechanism for the Anpatro or patisiran, this is a 5-component mixture. The siRNAs are shown here, which has the deoxy overhangs and 2'-O-methyl in the sites where to provide the endonucleolytic degradation sites, and these red balls are the RNAs, and they are packed into the lipid nanoparticles, and the key lipid is this MC3, which is an ionizable lipid, which has a pKa of 6.4 after the lipid nanoparticle is formed, which has the stabilizing lipids like cholesterol and DSPC, and this pK is controlled by this PEG 2000 with the C14 anchoring. And we studied this over a period of several years and understood the mechanism, how this Trojan horse works. And this mechanism is going through by association after administration by recognizing the ApoE And once the ApoE protein is recruited, it is recognized by the LDL receptor expressed in the liver hepatocytes in this space of DC during the fenestration, and that helps the recognition very effectively, and that leads the endocytosis, and in the endosomes, because of the pH drop, that leads into the lipid destabilization followed by endosomalytic release, a bilayer structure changing into hexagonal phase structure and very efficient release. The two things which are very important to remember, because of this ApoE binding that leads into the efficient liver delivery, and because of the ionizable pKa head group, it leads into very efficient endosomalytic release and also kind of a proton sponge working on this. And this leads into the freedom realized, and this is the best endosomalytic release mechanism which is being now utilized in the case of mRNA therapeutics and also for some form of CRISPR-Cas therapeutics. Let me move on to the third platform of Alnylam, which is the GalNAc conjugate platform, which we worked for the past 15 years, which is going constantly improvement, and some of our publications are shown here. And this trivalent GalNAc, as you know, recognized by the acylglycoprotein receptor, expressed in hepatocytes in abundant number, 500,000 to 1 million copies per cell, and it's a high turnover because it's a kind of garbage cleaning mechanism of the system. The recycling time is 15 minutes, and it's conserved across species, and we are doing this as a subcutaneous administration. And you are going to hear a lot of chemistries behind siRNAs and how we are using some of these high affinity as well as low affinity modifications to control the off-target effects and so on. So let me move on from the RNAi platform into one slide showing the antagoners and microRNA mimetics. And this microRNA duplex is coming during the process of the dicer activation from the pre-messenger RNA, here shown here, pre-microRNAs. And this microRNA duplex, by binding to the protein, can control various biological processes. If we like that process during the controlling the disease, we can add that microRNA duplex in the form of short microRNA mimetics. Or when after the loading this microRNA into the organoid, and if it behaves like the siRNA, but it is causing problems, then we can control this the loaded microRNA by bringing an antagomer or antagonizing this. And that two processes are shown here. One is the microRNA mimetics, another one is the antagomer, and here the siRNAs understanding would be helpful. Here the antisense understanding would be helpful. And this is achieved by high affinity modifications as well as with the conjugates. Another very important mechanism is the splice altering mechanisms as part of the single strand antisense mechanisms. Apart from RNase degradation, and another possible mechanism which is not realized is the translation arrest, but the one thing which is realized and useful is the modulation through the splicing processes, which is shown here. We are controlling the introns and exon processes. And I will give you two examples from the approved drugs. The first one is eteplirsen. Here, this is useful for controlling the DMD, and this splicing oligonucleotide is shown here. When there is the splicing process leads to the stopping of the dystrophin protein synthesis because of these mutations happening in this region. One can introduce an antisense molecule against the 51, and that leads into the fully formed, the developed dystrophin, except for the truncated region where we are controlling through this splice modulator. So this is leads to a truncated but still functional dystrophin, which is very useful. And the chemistry used here is this a 30-mer morpholino backbone shown here, and this has been shown to be having a good uptake for the muscle where it is needed. An alternate compound for the spinal muscular atrophy is the methoxyethyl uniform oligonucleotide with the phosphorothioate backbone, an 18-mer, which is very successful in the form of this nusinersen or Spinraza. And this is controlling spinal muscular atrophy, as I mentioned. And in the disease stage, it causes into the defective protein missing the exon 7. Once we place the splice-altering oligo close in that region, the functional protein is reestablished, and that leads into the establishment of the cure, and this is by the intrathecal administration. I don't know what's happening here. And then the last example is the aptamer, and aptamers are where we are controlling the function of the proteins by making synthetic oligonucleotides. We will be hearing about this from SomaLogic, and these aptamers are useful for diagnostics and therapeutic applications, and they are developed to aim to rival antibodies, and they can also be used for targeting ligands. And as we know, the one example from the approved drug is the Macogen, which controls binding to the VEGF-165 for age-related macular degeneration. The chemistries involved are RNA chemistry in these two places, these two A's, and then 2' methyls for all the purines, and all the pyrimidines are 2' fluoros. And the pharmacokinetics is controlled by a 5' peg of 40,000 peg through the amino linker, and 3' exonuclease through the DT inverse linkage, 3' to 3' phosphodiester linkage. And this is again an intravitreal administration to control the macular degeneration. So this is a kind of a quick overview of all the 6 compounds which are approved and what are the chemistries behind. And I tend to go rather fast, and I'm over time by 1 minute, but I want to end with 2 comments. Have we solved all the problems now? No, that's not the reason why we are here. It is just the end of the beginning. The second thing, I always look back to the delivery problem. One of the lessons John Paul Baer taught me was we are still addressing the delivery only by a certain percentage, small percentage. So he tells his fellow chemists back to the bench. Thank you very much.